Hi everyone, I'm Constant, and I'll present our work LuxAR, a direct manipulation projected display to extend and augment desktop computing. This work was done with my supervisors Jerry Kazi, Sven Malakia, and Daniel Vogel. Let's first look at one of my friend's desktops. What we can see here, a very large monitor and several laptops. You may also have tablets and smartphones on the other side. So what we commonly have nowadays is we have multiple displays, devices to extend the desktop computing and coordinate and access more information. However, we have several challenges here, such as the constraint with physical space, the difficulty to optimize device placement, and the cost of having this huge amount of devices. People have tried various solutions to overcome these issues. One approach is using head-mounted displays to break the physical boundary. However, this can be tiring to wear for long periods. Another solution is spatial augmented reality, which uses projector camera units for projection mapping and transforms the physical surfaces into interactive displays. To extend desktop computing onto physical surfaces, some SAR systems use multiple fixed-position projector camera units to cover more surfaces, but their projection space cannot be adjusted once set. Steerable projector camera units can adjust the display by implicitly tracking users in the space or via hand gestures or voice commands indirectly, but still users cannot directly control the interaction. Handheld systems offer direct input but must be held in the air, causing fatigue. Therefore, a method to hold the system in space is ideal for long-duration tasks. LAMs are common interactive systems and offer various interaction opportunities. Some support projector camera units but lack input capabilities. Flashlight and lantern designs inspired handheld devices for virtual interaction, but they occupy one hand, making it challenging to establish sustainable augmented physical environments. Architect lamps offer flexible manipulation and maintain their pose after manipulation. They allow interaction using inputs attached or detached to this manipulation. However, the direct manipulation potential of architect lamps has not been fully investigated to extend our desktop computing. In this work, we build an LuxAR, a novel form of direct manipulation leveraging unique characteristics of physical lamp movement to extend and augment desktop computing. To build our prototype, we place a button inside and a pico laser projector inside the lamp and place multiple optical track markers at the bottom side of the lamp for tracking. We design multiple interaction techniques using architect lamp's physical manipulation characteristics. The first one is content positioning, where the lamp is a point device. User use the lamp to point at a window and then press the button to drag the window across desktops, physical surfaces, and devices. Releasing the button will drop the window at where the lamp points at. Therefore, when we manipulate the lamp to move the window across different surfaces, the content inside this window will change accordingly. When we place the lamp over a window and adjust lamp's height towards the surface, the level of details of the content inside this window will also change. We propose three interactions to augment objects and devices when we manipulate the lamp and see these objects. The first is temporary overlay. Temporary overlay is to temporarily enhance a physical object based on the content moved by the lamp. The second is permanent overlay, which persistently augments a physical object no matter what the content is and revealed by the lamp hovering. The third is temporary view, which is to enable users to expand a small display of the device using the lamp. When lamp stays stationary and not manipulated, we can perform different inputs commonly found on the desktop computing using, for example, pen to annotate information. We use touch on the surface or the devices to manipulate the information, or just use the mouse to change the virtual information directly. We will present three scenarios to demonstrate how LuxAR can be used in daily applications to extend our desktop computing. The first example is a calendar application. We can use the lamp to adjust its height, and then so we can change the calendar's view from weekly to daily or to monthly. We can also move the calendar application towards different surfaces for different purposes. For example, we can display our calendar to our colleagues by placing it onto the wall, or placing it onto the ceiling to show what the next event is and show a countdown timer, so both my colleagues can know when I'm not at my seat. We can also augment physical objects. We can move the calendar application towards the clock and show the events around the clock. We can also move the lamp over a keyboard and show the shortcuts of the application of the calendar application. We can also move the calendar application to the mobile device and have extensive views for the mobile device, so we can navigate to what had happened yesterday and what will happen tomorrow. The second example is a music player. We can move the music player from the service to the speaker to switch the audio output from our monitor or our display to the speaker. We can also move the calendar application by the lamp to different surfaces. For example, move it to the wall to decorate the surface, or move it to the ceiling to visualize the music and enhance the whole atmosphere in this room. The third example is a floor plan, where we can adjust the lamp's height to navigate to different layers of the floor plan. And when the lamp is stationary, we can use the pen to annotate the information directly on the table. We conducted a two-phase user study with 12 participants to evaluate our system with the proposed interactions and manipulations. In the first phase, participants had 3 generic applications and completed 15 tasks with LuxAR. In the second phase, they then explored the 3 scenarios we just mentioned. Through our studies, participants had different feedback towards our system. The first point is participants found the manipulation itself is quite intuitive. It's easy to move the virtual information across surfaces, but manipulation angles matter. It's quite easier for participants to manipulate a window from the monitor to the table, but difficult to move from the table to the ceiling. The second point is surface adaptation is influenced by both the content and context. For example, some participants noted privacy concerns when asked to share the calendar with the public, but none raised this concern for the music player example. And the ceiling was considered less suitable to show the calendar example because participants won't look at it. Participants had also varied opinions on the interactions based on lamp's height adjustment. Most participants got confused by this manipulation and had no clue how to use this manipulation to interact with the content. However, they found out the floor plan was a very good example to illustrate this interaction. But adjusting the lamp height will also change the lamp projected space size, which was a limited size and prevent the user from reading the information. As for the object augmentation, participants found these interactions very enjoyable and very interesting. However, they struggle with the job application, specifically when and where to release the button when they want to augment the object. There are also multiple challenges associated with other inputs when the lamp stays stationary. For the mouse input, the first point is the resolution in the lamp display is relatively low, so that it's a little bit hard to track the cursor with the lamp display. The second point is, as the lamp moves around to different surfaces, it is also difficult for them to tracking where the cursor is when the lamp points at a new surface. While participants were very familiar with touch inputs on device and surfaces, they have different feedback. For example, some participants would prefer just pinch on the surfaces, but for more simple actions such as just tap, they will go back to the mouse and keyboard. And they reported that the touch does not feel the same on the surface and device. Then there's latency issue with the touch on the surface. We do not have additional feedback with the pen. As participants' main focus was on high adjustment with our third floor plan example. Overall, participants were able to propose different scenarios for our system. Most of them focused on collaborative environment using the LAMP as both an input and output tool to play multiplayer games and share information to others across devices. After exploring our three applications, two recommended context-aware applications such as showing the information based on where the lamp is located, and two suggested to show information based on what the lamp is pointing, and then move the information to other spaces. Overall, participants found it intuitive to use the lamp as both an input and output tool, but faced challenges in operating the systems in specific lamp orientations. Participants had different feedback on how projected content adapt to lamp heights, and setting was less favored compared to other services. They asked for more obvious interaction indicators or visualizations during manipulation. Therefore, we revisit our designs and then think of several solutions for futures. As some aspects of the lamp manipulation may be challenging, one solution is to change its mechanical designs. For example, we can replace current joints with spherical joints or 6x force torque sensors with locking capabilities. We can also attach wheels on the base of the lamp for easy dexterous movement. Designing the attached or detached interaction for direct manipulation systems require careful thought to accommodate different contexts. First point is the explicit control of limitations or direct control allows users to decide where to display information and what the information to display. This makes interaction more focused and avoids distraction. However, this may also limit people from browsing information outside the chosen augmented area, which is commonly seen in many SR systems with one ProCam unit. The second is the net selling was found next favorite by participants. It may due to the fact that it's next explored with our current technology and system. It could actually serve as a very nice display to convey ambient information, and LuxAR creates such an opportunity. The third is for direct manipulation SR systems, high adjusted interactions are less suitable for content with high text density, as the size changes or shrinks, as the display size changes or shrinks, it's hard for participants or for users to read the text. And the last point is it's important to inform users about the interaction state and guide them on when, where, and how to initiate interactions. This is especially important to augment objects and devices. As for the detached interaction with stationary lamp, we found that touch and pen work on the table, but not very suitable for the walls and ceiling. Mouse is generally preferred, and its cursor visibility need to be enhanced during direct manipulation of the lamp. The third point is, while mobile device support touch inputs, its high-resolution touchscreen makes it better holder for content. For example, we can show high-fidelity information on the touchscreen of the mobile device and place the buttons around this device using our lamp. To conclude, we contribute LuxAR and articulated ProCam lamp to establish a promising way to connect current desktop computing with the surrounding physical desktop space. Thank you.